In this video, we talk about how distance is represented both geometrically and algebraically. And so the algebraic representation of distance, if you're given two real numbers, A and B, and you want to measure the distance between them, and you're not sure whether or not B is the larger number or A is the larger number, you just want to take the difference between the two and put absolute values around it. So whenever you see an expression of this form, which you're going to see a lot throughout this course, where it's a difference of two values inside an absolute value, I want you to be thinking of geometric distance. So a lot of times you're going to be working with different expressions, and it's going to be useful to draw pictures associated with them. If you have the absolute value of just one number, absolute value of x, you can think of that as the distance between x and 0. So here is my number line. I've got x on it, and I have some other real number y, and we're just saying that this distance right here is the absolute value of x, and this distance is the absolute value of y. Now, since we're going to be working a lot with algebraic expressions, it's helpful to have knowledge of certain rules about how absolute values behave. And one of the main rules in this class that you're going to use all the time is the triangle inequality. So this you need to commit to memory. So I'm going to write it out for you. Basically, it's a double-sided inequality, and it has to do with what happens when you do the operations, when you add two numbers inside the absolute values versus splitting them apart. So think about this. You have two real numbers, A and B, and either they are the same sign, so they're both negative, or they're both positive, or they're opposite sign. And if they're opposite sign, then when you add them together, that's going to decrease the overall magnitude of the value that comes out of the absolute values. Whereas if you were to throw out the signs first and then add them, you're going to end up with something larger. So when you split absolute values apart, you either stay the same in the event that A and B are the same size, same sign, or you get something bigger. There's also a rule about how it works for subtraction. And this side of the inequality, we're not going to use as often in this class. You'll only see it a handful of times. I'm going to call these inequalities inequality 1 and inequality 2. So number 1 is the one that you really are going to be using all the time. So the way that this proof is going to go, we will actually prove 1, and then we'll use the first inequality to prove inequality number 2. So let me write that out. We will prove 1 and use 1 to prove 2. And there are some important facts that we're going to use in our proof. So the first one is that when you take the square root of a number squared, x squared, you get, well, we're probably used to seeing this as plus or minus x, but really what we mean is absolute value of x. Depending upon if x was a negative number, you're going to get the absolute value out. Square root of a number squared should always be a positive number. And then if you have a number x and you want to compare it to its absolute value, then those are either the same or x is going to be smaller in the event that x is negative. And so we're going to use this inequality. So in order to prove inequality 1, we're actually going to prove a different equivalent statement. So to show 1, we will show instead that a plus b quantity squared is less than or equal to taking the absolute value of a plus the absolute value of b and squaring that expression instead. And so you should take a moment and pause the video and ask yourself, why is it that this expression here, why is this equivalent to showing 1? Well, you can just apply square roots to both sides, and in applying square roots to both sides, we're using this first fact here that when you take the square root of x squared, you get the absolute value of x. So in applying the square root to both sides, let's write this out. It's going to yield the following. Remember, when you take the square root of a squared expression, you're getting absolute values around everything, but for this expression that we have on the right, the outer absolute values are redundant since what's inside already has to be non-negative. So we can drop them. The other thing here that I want to point out is that we technically haven't said why this is true. We've taken square roots of both sides and we have to ask ourselves, well, why is the inequality preserved? That's not true for every function. For example, if I were to apply the cosine function to both sides, that wouldn't necessarily, if I start with a being less than or equal to b, that doesn't mean cosine of a is less than or equal to cosine of b. So you want to ask yourself, well, what property about the square root function are we using here that justifies the preservation of the inequality when you apply the square root to both sides? And the answer to that is just the fact that the square root function is increasing. So because the square root function is an increasing function, it means if you start with two values a and b that are ordered one way and you plug them into an increasing function, they have to maintain that order. Okay, so our goal, remember, we said we're going to try to show this inequality instead up here. And in order to prove that an inequality is true, you can't just write it down and then say nothing goes wrong and so it must be true. You have to work with one side and arrive at the other. So in doing so, it's probably helpful to write out what each of the expressions look like. So let's expand both sides of our expression. So I'm going to kind of do this in a chart. So we've got, on the one hand, we've got a plus b squared. And on the other, we've got the absolute value of a plus the absolute value of b, quantity squared. So if I were to expand this out, I'm going to get a squared plus 2ab plus b squared. And then over on this side, I'm going to get the absolute value of a squared plus 2 absolute value a, absolute value b, plus the absolute value of b squared. And so now I want to try to compare these expressions to one another and try to understand where the inequality relationship comes in. Well, the first thing that we can note here is that if you have an absolute value and you square it, it's the same thing as just squaring it. You don't need the absolute values. Those are redundant. So I can drop them. And now what we see is that we have an a squared and we have a b squared on both sides. So the key to understanding where the inequality comes in is to ask the question, how does the term 2ab compare to 2 absolute value a, absolute value b? Well, if you go back up to one of our facts, remember we pointed out earlier that when you have a real number, it's always less than or equal to its absolute value, depending upon whether or not x is positive, negative, or 0. So we're just going to get that direct inequality here. We're going to use the fact that we know that a is less than or equal to the absolute value of a, and we also know that b is less than or equal to the absolute value of b, and so we can just make replacements. Overall, 2ab is going to have to be less than or equal to absolute value a, absolute value b, and that's our proof. So here I'm going to actually write up a formal proof of 1. So technically the triangle inequality is a universally quantified statement. It is true for all real numbers a and b. So I'm going to let a and b and r be arbitrary. And then I'm just going to write out the inequality that we get. So when I look at a plus b squared and I expand it, I'm going to get a squared plus 2ab plus b squared. And then I can slowly try to start making replacements so that I can kind of, I'm starting here and then I'm going to kind of go up and go backwards and arrive at the other side of my inequality. So the first thing I can do is I can make a replacement and say, well, that's the same thing as writing the absolute value of a squared plus 2ab plus the absolute value of b squared. And then I can just make my replacement here. This is going to be less than or equal to, well, I know a is less than or equal to absolute value of a, so when I go ahead and I make that replacement, I arrive at that expression such that when I factor it out, I have exactly what I want. You may want to make a note here. This is since a is less than or equal to the absolute value of a, and b is less than or equal to the absolute value of b. And then factoring this, we have the expression we were looking for. And then applying square roots to both sides. That yields exactly what we want. The absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. And that's exactly what the first triangle inequality is saying. So now we need to show the second inequality, and we had said earlier that we're going to use the first one that we just proved in order to show this one. And in trying to prove this, it's going to illustrate to us a technique or a strategy for solving problems that you're probably going to want to employ and use as you try to solve other proofs about other things in this class. And the idea behind it is we look at it and we say, well, what's funky? What's bothering us? And for me, when I look at this, I think, what's up with these outer absolute values on this first term? Those are bothering me. And that's going to be the case in a lot of problems. There's going to be an aspect of it that's funky, and you're going to say, oh, I don't like that. I would know what to do if I didn't have that there. So oftentimes what you want to do is to just say, well, let's get rid of the funky thing. Let's see if we can prove this problem without those outer absolute values. And then go back and ask, well, how do we bring them back in? So that's what we're going to try to do. So let's try to show that the absolute value of A minus the absolute value of B is less than or equal to the absolute value of A plus B. And so we will worry about the outer absolute values later. Okay, so now we have this new expression that we're focused on. And remember what we said, and I'll write this out here in the corner. We said that we have this other inequality that we can already use. We know that when you take the sum first and then the absolute values, that's less than or equal to splitting it apart and doing the absolute values before you add together. So this was inequality 1. Okay, so now we look at this one and we ask the question, well, how is this different from what we already know how to do? So what I mean is I want us to be comparing and paying attention to the inequality we know and the inequality we want to show. And the question is, what's different? If I just look at this, the overall structure, a big thing that I see that's different is the subtraction, right? In this second one that we're trying to show, we're subtracting instead of adding. So a natural question to ask is, how can I rearrange this inequality so that it looks like addition instead, so that I can try to see how this is related to the first triangle inequality that we already proved. So I am going to, if you want to take subtraction and make it into addition, the easiest thing to do is to just rearrange. Now, remember, I can't assume that this inequality is true. I am just trying to come up with a different way of representing the same inequality so that I could establish that inequality as being true. So equivalently, I would like to try to show that the absolute value of A is less than or equal to the absolute value of A plus B plus the absolute value of B. So this new inequality, this is what I want to show. Because if I can show that, then rearranging, I will have shown the inequality that we are looking to show, our other highlighted inequality here. So now notice that this is starting to look similar to the triangle inequality that we already have. But it's a little bit different because of where the expressions are sitting. But we need to remember that the triangle inequality is true for all real numbers. So I can use any expression of real numbers and I can apply this triangle inequality number 1. So it kind of looks like what I've got right now is something of the form x plus y less than or equal to the absolute value of x plus the absolute value of y. And what I'm doing here is I'm trying to say what's x and what's y so that I can rewrite or rethink this inequality I'm trying to show in terms of the triangle inequality that I already have is true. So I want you to pause the video and see if you can come up with what x should be and what y should be. And then we'll come back together and I'll show you how to do this. Okay, So looking at it, you can see sort of there's this one-to-one correspondence, and it seems like, maybe A plus B should be X and B should be Y. However, if I let B be Y, then when I go and I add X plus Y, I would have A plus 2B, and that wouldn't work. I need to make sure that when I get X plus Y, I'm going to get A. So here we're looking for an X and Y such that X plus Y needs to equal A. And right now we can say, it looks like X is A plus B. So what's Y? So that X plus Y equals A. Well, if you sub in, you get that Y has to be negative B. And that seems a little bit funky because we're introducing a negative sign. So let's go back and see if that makes sense here. So what we're saying is, if I think about X plus Y, that's going to be A plus B plus negative B. And notice that is exactly A. That's what we're looking for. So we've got the absolute value of A, and we've been clever about how we write it. Essentially what we've done is we've taken A and we've added 0 in a fancy form. This is a common technique that we're going to be using throughout the class. Whenever you don't see something in an expression and you want it to be there, you can force it to be there by adding and subtracting the same value. So I added B and I subtracted B. Now I'm going to apply the triangle inequality. And the triangle inequality says this, and I'm using triangle inequality number 1, the one we've proven. This has to be less than or equal to the absolute value of splitting things apart. So I've got absolute value of A plus B plus the absolute value of negative B. And notice that's the same thing as the absolute value of A plus B plus the absolute value of B. And that is exactly what we were trying to show. I've started with the absolute value of A, and I've arrived at that being less than or equal to the absolute value of A plus B plus the absolute value of B. So I'm done. Because after I rearrange, I have exactly the inequality I want. So if I wanted to write this up as a proof, I could say proof. I'm going to let A and B be real numbers. Then I can say the absolute value of A is really A plus B in absolute value minus B, or plus negative B. And then I can split it apart using triangle inequality 1, which we've already proven, so we can use that. And that's equal to exactly what we want. And then I can say rearranging, we've shown that the absolute value of A minus the absolute value of B is less than or equal to the absolute value of A plus B. Now we have to take a step back and say, are we done? Did we prove what we were trying to show? Remember what our goal was. We were trying to show this inequality number 2 up here. And notice we're not quite done because we need to think about how the absolute values are supposed to come back in. So what happens when I add the absolute values back in? It may be helpful, and so this is going to be kind of a break in our proof. It may be helpful to write out what the definition is of the absolute value expression that's funky. Remember how absolute values work. When you drop the absolute values, you just get what's inside when what's inside is non-negative. Or you get the negative of what's inside, which is actually just subtracting in the other direction when what you have absolute value of A minus absolute value of B when that's negative. So really what we need to do is we need to be thinking about this argument in terms of cases. Case 1, we have already done. The case when you drop the absolute values, when you just get absolute value A minus absolute value B. We now need to show that it's also true when we drop the absolute values when the expression inside is negative. So we also need to show that the absolute value of B minus the absolute value of A is less than or equal to the absolute value of A plus B. That's the way I can show that when I put the absolute values around the entire expression, it's less than or equal to the absolute value of A plus B. Well, notice that this inequality that we're looking to show is really similar to the one we've already shown. It's just that B is playing the role of A. So I'm not going to go through and give the exact proof, but or write it up formally, but if you go and you look at the absolute value of B, this time we're going to add A and subtract A. And do the same thing. It's going to be analogous. So that's less than or equal to the absolute value of B plus A plus the absolute value of negative A. And I could rewrite this as A plus B plus absolute value A like that. And then rearranging, we get what we want. So since both orders of subtraction lead to the inequality being true, we're allowed to put the absolute values back on. So really the high level here is we're saying since we know, or we've shown that the absolute value of A minus the absolute value of B is less than or equal to A plus B, and the absolute value of B minus the absolute value of A is less than or equal to A plus B in absolute value, then we can put the absolute values back on around the expression and conclude that inequality holds. You might be wondering why this is called the triangle inequality. I don't see any triangles here. Let's actually try to see if we can figure out how this is the triangle inequality. So imagine I have a triangle and I'm going to label its vertices A, B, and C. The triangle inequality is actually talking about, it's a way of doing, if I could think of this as I'm at A and I'm going to measure the distance to C. Now, the fastest way to do that would be to walk along this bottom edge. And that would just be the distance A minus C in absolute value. Or I could go there by walking this direction and taking the other legs of the triangle. And if I did that, my distance, I would have to do the distance I would have A minus B here in absolute value, and I would be adding to that the distance of walking from B to C. And so the triangle inequality, if I put this together, we're saying that if I want the distance A minus C, that should be less than or equal to walking through the point B. And if you think about what this is saying, in terms of like how does this fit in with the original way that the expression for the triangle inequality is represented, A minus C is kind of playing that role of, this is like our X plus Y, this is our X, and this is our Y. So in this case, if I try to figure out what X, so we're saying X is really A minus B, and then Y is really b minus c. And then we're just splitting it apart. Notice that if you collapse this, this is another way of writing a minus c. Again, if you don't see something present inside the absolute value expression, you can add and subtract something in the form of 0. So I add and subtract b to make it look like that. So that's why it's called the triangle inequality. So the last question I want you to think about, and so I would pause the video and think about this, is there a relationship between the absolute value of a minus b and the absolute value of a plus the absolute value of b? Right now, we know that there's a relationship when what's happening inside the absolute values is addition. But what if I change it to subtraction? Can we say anything about that? So pause the video and then I'll show you the solution. So it turns out that yes, there is a relationship. Remember that subtraction is really just addition, and we said the triangle inequality is true for any real number. So in particular, if it has to be true for a and for negative b. So I could think of this as a plus negative b. Now it looks more like the triangle inequality, and since we know how that works when there's addition on the inside, we can split it apart, including that negative sign there. And remember, absolute value of negatives, well, it doesn't matter. We can get rid of the absolute value. So it turns out that it's also true that when you say a minus b in absolute value, if you split that up using addition, it's the absolute value of a plus the absolute value of b. This may be necessary in some of the things that we do in this class. So just because you see subtraction doesn't mean you can't use the triangle inequality. You just need to think a little bit more cleverly about it. Perhaps think of it as plus a negative instead of subtraction.